Welcome to the fifth most scientific workshop of the International Forum of Agricultural Robotics. We are pleased, Stephane and myself, to welcome you, and we will have the opportunity today to talk about how robotics can help agroecology. This workshop is co-organized by ROBAGRI and INRAE, the ROBAGRI Association and INRAE, and before starting we will have a short overview of these two organizations for introducing the day. So I let Stephane introduce ROBAGRI.
Thank you, Roland. So I'm going to give you a brief outlook of the association before Roland introduces the official scientific forum. We are the association. I'm Stephane, Duran, product manager from the association. So our association unites the sector from the research to the machinery sector to the farmers in order to represent and accelerate the sector. I don't know if it's the next slide. If you can put the... Thank you. Then we are 88 members. Our mission, we were created in 2017 with a chairman, with Kuhn as chairman at the beginning, and the initiative was set by AXEMA and INRAE at the beginning. And now we've got Agriculture as a chairman with Christophe Aubé. In fact, we've got three objectives, which are to represent the sector, then work together. We've got NDAs with our working groups, then we share knowledge, and then we foster a vision for tomorrow agriculture. Next slide, please. We can go. We can jump on this slide as we have to go fast. Yeah, please. We can go. Take next slide, please. Yeah, a few actions. So they range, from the technical part to the farmers' needs and to the farmers' needs. A few actions, we did set up we did enable the farmers and the machinery sector to test prototypes in the fields. We did set up this, it was a 20 million envelope. We did set up this envelope with AXEMA. And we also had some hard work since the beginning on the safety aspect with a common group with AXEMA and joint with SEMA, and Cédric Seguineau from NAIO was leading this for us with Guillaume Bouquet. And when you go to the other side of what we do, in fact we work to give benefits to farmers. We've got now an envelope, a 20 million envelope on a 5 years period to pilot in order to get more accurate machines on the market corresponding to the farmers' needs. Yes, next slide, please. So I can give you a few examples of our machine. What you can see is that they're very diverse. You've got from the breeding cattle sector to the vegetable ones. You've got some feeding machines, for example, from Kuhn and Gentil. You've also got some handling machines from Manurob MX, and as well as machines in the field sector, such as Kuhn one and NAIO ones, and where you've got a wide offer, and it's in the wine sector, and we can point out a few machines which are specialized, such as Osiris, which is on the irrigation and so on. So yeah, next slide, please. A few overview of our members. I want to point out that we are open to the foreign members as long as they contribute to the development of the French market on the long term. They can apply. So we've got some foreign members. Next slide, please. As well as we've got suppliers with also key players that you may know. Then we can move on to the next one, and this is a research and applied academics agricultural sector. And then on the other slide, please, thank you. This is a college. This is a farmers' college. We've got some cooperatives, also some distribution for the machinery sector, and also chemicals. So this is a sector we want to develop. And thank you for your attention. Then I'll give the Roland will launch the official sector.
Thank you very much, Stephane. Just take the opportunity to present briefly what can we do in INRAE. I'm sorry, I have not a good presentation, but we could switch to my laptop if it's possible. Yes, thank you very much. So a lot of people know the National Research Institute for Agriculture, Food and the Environment. We are working on several big aspects of agriculture and feeding people. And we organized this workshop at the unit TSCF in the center of France here. And we are a small unit that are trying to develop new technologies to achieve agroecological principles. Then we work on IoT, we work on equipment autonomy and robotics, about environment analysis and understanding. And we do our best to develop new implements and practice for ensuring transitions. And we also tried to investigate the usability of these new technologies. And with ROBAGRI, we are involved in several big projects in France because we have a big plan in order to develop this technology for agricultural transitions. And then we are working on the Grand Défi, Grand Challenge, robotics for agroecology, that maybe the first speaker will talk about. We are involved also in a big strategic plan about agroecology and ICT. And we are involved in this framework in a big national project about small robots to achieve new agroecological itineraries. And I make some advertisements for our robotarium, which is a vivarium of robots. And if you go on the stand 7 during the FIRA, you will see some of our robots, and we can discuss about all that. And now, today, our work is to talk together and to have the opportunity to see the last advances in terms of robots for ensuring ecological transition. So we will talk about how robots can help to make new practice, how robots can recognize the environment and improve decision-making to work in such areas, and how robots can be integrated into the farm. And then we're going to start with this first station, which is called the taking part of robots to achieve agroecological routes or itineraries. And we will start right now with our first speaker, which is Cédric Seguineau from the ROBAGRI Association, who will talk about reflection around the construction of robotic crops routes for agroecological purpose. Thank you so much. And I let Cédric start this 5th workshop.
Okay, thank you very much. It's really a pleasure for me to open the session today. as Stephane and Roland have said, I've just been freshly appointed at the head of the Grand Défi. Roland has said Grand Challenge in English. I'm just going to keep the French word for that initiative, Grand Défi de la Robotique Agricole, which is a national initiative to try to accelerate and to consolidate the emergence of robotics in the field and to make it a reality. So this morning I'm going to try to explain how robotics and agroecology can work together and what we are going to do in the frame of the Grand Défi in order to try to accelerate and to facilitate the emergence of new practices close to agroecology. And at first, I want to thank my co-author because I've been freshly appointed. Before that, I was in NIO, and all of the work is mainly their contribution. So thank you for Marine, Marilys, and Xavier, who are part of the Grand Défi right now. So let's start the session with a very optimistic slide for the day. You know that concept about the planetary boundaries, I guess. So just to make a statement that over the last years, the activity seems to be not really sustainable, especially for agriculture, which is one of the main contributors to the concept of planetary boundaries. And what we can see is that on several aspects, several dimensions, we are crossing the line, especially about biodiversity. Indeed, over the last decades, agriculture has been developed based mainly on the use of pesticides to do and to ensure the yield. Here you can see the use of pesticide over the world. What we can say right now is that it leads to a non-sustainable pressure on the environment, and if we want to avoid some collapse, at some time we need to change. I'm not going to go in detail. There is a lot of literature about that subject. But the question is how we are able to produce more with better quality and with less inputs, less resources, less soil. And that question is the crucial question for everybody working in agriculture. One first answer is based on what can be brought by digital. Indeed, if we are looking at what we call precision agriculture, the principle is quite simple. Instead of looking at the field and just applying inputs, chemicals over all of the field from an homogeneous point of view, we are going to take care of the plant itself. Plant by plant, we are going to look at its needs, and we are going to provide just the accurate input for that. The point is that if you want to do that, you need to have a very good understanding of the interaction of the plant with its surroundings. You need to have a good knowledge about agronomics, for sure, but also you need to have access to data. And to do that, you need to rely on the new technologies which are associated with what we are calling digital. The point is that even if you apply big data and numerical technologies, and you are able to do precision agriculture to make it a reality. If you look at this kind of article, for instance, they are just happy because, I quote them, we are going to be more efficient, we are going to reduce the arduous task for the farmers, and so on. So that's a good point. But we are still on the same trajectory. So the question behind that is that if we just push the model further with the help of digital, are we going to go in the world just a few months or a few years after, or do we need to change totally the system? So precision agriculture by itself is not a total answer. We need to find something else. Over a few decades, there is what we are calling agroecology, which is a theme for today. So I'm not going in detail about the definition of that. What I can say from now, I'm not an agronomist. What I can say is that it is based on the fact that we are going to use natural principle, and we are going to study agronomics and to take benefits of natural interaction between the plants, between the soil, to take care of the plant by using resources as they are on the field. It is based basically on biological regulation. It is based on agricultural practices where we are going to use auxiliary plants, we are going to use additional plants, we are going to rely on living soil, we are going to respect basically the functionalities of the system. And it is based on something which is complex per nature. So to do that, you are going to have access to data, for sure, but you will have also to act and to take care of the soil at the plant level and to take care of the interaction around the plant. So you will need to have access to a lot of data, a lot of labor also to do such a work. And there is still a lot of uncertainties about our ability to use such an approach at scale. Keep in mind that we need to provide food in quantity for all of the people around the earth. So if we want to change agriculture and to make practices like agroecology as mainstream practices, we need to be sure that we will be able to provide food safety, food quality, food quantity for people. And there is still a huge question mark about that subject. Some example of practices, and this one are very interesting because maybe robotics can be used very straightforward on such an approach. For instance, when we are talking about strip cropping, we are going to take benefits of interaction between several plants on the same field. So to organize the practices, the agriculture, we can put in place several systems like strip cropping. We can also go to multi-cropping and pixel cropping. That is to say that we are going to mix all of the plants, all of the crops on the same field to take care of the interaction. The point is that in that case, it's become very difficult for the equipment to be able to make a distinction between all of the plants and to apply the proper care at the proper plant at the proper time. We can also try to remove interculture by working on several plants on the same field at different time and to be able to take care of one crop instead of the other at a time. That's just some example. What we can say here, it's just an overview published by the CTFL, is that there is a lot of studies which has already been done about agroecology, and a lot of practices are very promising. But the point is that in most of the time, you will need to take a lot of manpower to put in place the practices. It's quite tedious, and most of the time, there is a lack of adapted equipment to perform mechanically the task or to facilitate the task. So for most of the approach, we are in some kind of dead end as long as there is no push to put in place a proper strategy to help farmers to deploy these techniques. And maybe that's where robotics can help. On the other hand, as Stephane has said, we have several robotics already on the field, already performing some tasks. Most of them are performing weeding, but we can also have other tasks performed autonomously by the robots. And the point is that we are going to evaluate how we can try to work together robotics to serve agroecology in the frame of the Grand Défi especially. The point is that we are quite sure that robotics can be used especially to try to develop preventive action, to try to help for pest control by avoiding the use of chemicals, to try to take care of plants when we are talking about pixel cropping or strip of crops. So the target of the Grand Défi is to evaluate what will be the potential of the robotics for agroecology. So basically, there is need for complexity, as I've said, diversity, agility, and robotics is one of the good technologies to do that, because it is, by definition, most of the time quite versatile. We can have different strategy, we can use digital, we can try to use artificial intelligence, and so on. So technologies could be an answer. It is not the answer. I do not want to say that. Robotics is not going to be the only answer to do agroecology. Absolutely not. But it could be a convenient tool to help farmers to deploy at scale some practices. And keep in mind that when we are talking about robotics, it is not something which is good for the environment by definition. If you are going to look on the FIRA, you will see a lot of robots working with electrical engine, performing mechanical tasks instead of using chemicals, or trying to make very precise spraying to avoid the use of large amount of pesticides. Nonetheless, that's not something which is obvious. You can have some example of robots which has been developed not for environment, but just to take care about labor shortage, and that's another reality. And you can also try to make autonomous units just to avoid to expose the farmer to chemicals. So in most of the case, the robots has been developed to answer to specific needs in the fields, but not for environment. And we are lacking a method to be able to evaluate if, at the end of the day, that robot is good for the planet or not. That is to say that if the impact of that equipment has been better, higher, or less than the conventional practices. And to do that, if we do not have a method to make such an assessment, it will be very difficult at the end of the day to be able to be sure that we are going on the good way. Keep in mind, for instance, the example of electrical car. During quite a long time, we have quite discussion if it is better if you take into account the manufacturing process and the resources which are needed to build the batteries, for instance. Is an electrical car better for the environment than a thermic one? And the answer is yes, in some cases, if you take care about the amount of resources which are used to build the car, and if you use it enough over its time before just going on another car. So it will be exactly the same for the robots. There will be some condition to ensure that at the end of the day, when you are going to look at all of the impact on the resources, on the emission, on the waste management, at the end of the day, the use of this material, of this equipment, will be better for the planet than what we are going to do before. So there is two aspects when we are talking about robotics. The first one is, are we going to develop new functionalities, and agroecology can be developed with robotics? Maybe. And the second point is that as soon as you look at new robots, you need to take into account that it has an impact. It is a new technology, and that impact needs to be assessed. And the fact is that we do not know exactly how to do that. One first approach which has been studied in the frame of the partnership with INRAE, in the frame of ROBAGRI, has been to apply the life cycle assessment method to the robotics. A few years ago, we have made a statement that there is no studies of such studies available in the state of the art, and we have been the first with Marie-Lise Pradel in INRAE to publish LCA on robotics. We have made a comparison of a TED, which is a NIO solution for weeding in the vineyards, and a conventional tractor. The base of the approach is to encompass from a system point of view what you need as an input, what you are going to consume to work on a specific functional unit, and what you are going to emit from that. And you make a balance of the input and the output, and at the end of the day, you are able to evaluate some contribution on several aspects, like global warming, eutrophication, human toxicity, the use of mineral resources, fossil resources, and so on. Quite useful. For instance, here is an example. As you can see, it seems quite difficult at first to understand what you can see, but if you go in detail, in the green circle, for instance, you have a comparison. The two first bar is the tractor impact on the global warming, and the two small bars after that are the impact of TED. The main difference between the two is in that part, that the contribution of the gas emission, just because in that case, TED is electrical powered on the field. On the red part, for instance, that's the impact on human toxicity. And in that case, you can see that the impact of TED is higher than the tractor. Why? Because human toxicity is mainly due to the manufacturing of the equipment. And in the case of TED, it is mainly used for weeding. That is to say that when you are going to use during 1 hour TED instead of tractor, you are going to use more, virtually more of the TED than of a tractor in that case. So that's quite useful, such a tool, to help manufacturers to do what we are calling eco-design. That is to say that they are able to understand what is the impact, what are the most impactful part of their robots and of the use of their robots. And in that case, they will be able to try to develop strategy in the design, in the development, to diminish that impact. But it's also a proper guideline to make eco-design on the practices, because in that case, for instance, we have been able to evaluate the impact of the shape factor of the field on the results. It appears that in some cases, when you have shorter row on very large field, the contribution of the use of the robots will be higher just because of the U-turn. So it just gives some figures to help people to understand how to optimize and how to diminish the impact of the equipment and the impact of the practices. The point is that such an approach is not something which is enough. It is just a first step. At first, because to do such an approach, you need to have a baseline. And to have a baseline, you need to have access to some data. In the frame of the studies we have done before, the point is that we are lacking some data on tractor. At first, we have used what we call a LCI, so an inventory of the life cycle, which is based on data coming of 20 years ago of tractors without any electronics on it. Quite weird if you look at the current tractor. So at first, there is a strong need to be able to share data about technologies, about the way they are built, about the amount, for instance, of aluminium, amount of electronics, and so on. So there is a lack of references, basically, if you want to make some comparison, which is useful for you if you want to make some eco-design. So basically, if you are producing several robots, several solutions, you can make a comparison internally, looking at your first prototype. But when you are a startup and you want to try to make good from the first attempt, in that case, you need to have access to some references. The second point is that with robotics, we are going to have quite a lot of new additional services which were not available at first. When you are looking at pixel cropping and so on, it will be quite difficult to evaluate what are exactly the new services and what is the added value. And in that case, you need to define properly the functional unit if you want to make some comparison. So even on a conventional system, it's quite difficult to have access to the references. With additional services and multifunctionality, which are at the heart of what the robotics can deliver, in that case, it will be quite challenging to do that. So we need to develop method to be able to handle that. Another very important point is that LCA is global per nature. You are not able to evaluate the local effect of the, especially on soil compaction, for instance. If you are using heavy equipment, you are going to compact your soil, you are going to have quite a negative impact on the living soil, and it's going to be difficult to assess what will be exactly the relationship between the weight of your machine and the chemistry of the soil. So in that case, there is other method to apply to take care about local effect. We are talking about soil compaction, we are talking about pollution, local pollution, the exposure of people to chemicals, to inputs, and so on. So all of that need to be further assessed and need to be encompassed if you, at some time, you want to have a global overview of the impact of your equipment on the environment. And basically, we are just talking about environment with LCA. When we are talking about agroecology, we are talking about sustainable practices. We are talking about something which is also better from a social perspective, especially for the farmer. So in that case, it's quite important also to encompass and to put in place indicators which are, from a social and economic point of view, quite relevant. And it will be another point also to be able to make a comparison between new technologies like robotics and the impact of, and to make a comparison with conventional machineries. And what is going to happen when you are going to mix all of the technologies? If you are using a conventional tractor, you are going to put on it new technologies, digital, you are going to perform several tasks with smart equipment. What will be the difference with robotics? So in that case, the method needs to be reliable enough to take care about robotics, smart equipment, conventional equipment. Basically, it's something which needs to be applied at the farm level and not just at the equipment level. So all of that, that's quite challenging. And for sure, we are just at the beginning of the research on this subject. That's one of the reasons why we have decided to launch the Grand Défi. So what we intend to do about agroecology is to be able to accelerate, basically, the development of robotics in farm. And to do that, the target is to help to accelerate the transition toward a sustainable agriculture. But for sure, agroecology, it's still at the research level. There are some practices we are quite convinced that with robotics we will be able to go at scale, for sure, and we are going to help for that. But there are several aspects. So at first, in the frame of the Grand Défi, we are going to take care of agroecology practices. We are going to push the research to try and evaluate how robotics can help to put in place new practices based on agroecology. So we are going to found mock-up, we are going to found collaboration between manufacturers and research institutes to be able to test, in some cases, without any idea of the market behind that. At first, we are just there in the research field. We need to test and evaluate if robotics can help and on which practices it will be the most efficient solution. So that's the first stage of the Grand Défi. And the second stage is on a more short-term approach. On that second stage, for sure, we need to provide to manufacturers solutions right now to help them to design and to deliver equipment with a known impact on the environment. Because at the end of the day, you cannot push robotics for agroecology if you are not able to be sure that the impact of your equipment is not going to be overkill. You cannot put a Tesla to work on your field. So we are going to deliver to people test capacities. We are going to work on the method. I've described all of the challenges to that. So we have several actions to work on the method, to work on the test capacities, to be able to deliver, to manufacture a framework to go further, faster on the development, and also to provide to the farmers some references and to be able to understand where they are when we are talking about environmental impact. So we are going to help them to assess what is the impact of each equipment and what will be the impact of their choice to change and to choose new practices. And for other stakeholders, also, we are going to help them to provide to understand what are the new values provided by the farmers, by the new practices. Keep in mind that if you are able to collect some data, for instance, that's not only useful for the farmer, it could be also useful at the territory level to understand, for instance, the climate change and so on. So all of this added value, not only for the farmer, need to be at some time highlighted. And we are going to push that toward public policies, toward other stakeholders, to be sure that at some time we are able to understand who is going to pay, basically, for this new equipment. So just as a conclusion, at first, what we can say is that there is for sure a very high pressure to change the agriculture. Agroecology may be an answer, but there is still a lot of uncertainties about our ability to go at scale with such practices. During that time, robotics is already a reality on the field. So we need to help manufacturers and solution providers, basically, to develop something which is eco-design and to help them to understand what is the impact of their solution globally on the environment, on the social and economic aspect. So we are going to put in place a toolbox to help manufacturers, to help farmers, and to help researchers to go further and faster on agroecology. Thank you very much.
Thank you very much, Cédric, for this nice talk and very hopeful. While the next speaker is putting his stuff on the desk, maybe we have the time for one short question, maybe two. Yes.
Hello, Tom Allen Stevens, a tech farmer in the UK. Cédric, it's all very worthy, this idea of agroecological approach to robots, but aren't you worried that it's going to stifle innovation? I mean, if Henry Ford was given the opportunity, was told that he had to consider resources when he was rolling out the first Model T, it would never have come off the production line. We are struggling at the moment to actually find we know the need for it, the value from them, not necessarily the ecological value. So how do you deliver innovation at the same time as agroecological value?
That's a very large question. I'm not sure that that's a short answer. Now, for sure, we need to understand that we need to have a split between the research about agronomics, agroecology on one stand, because if we put in the bag all of the aspects at the same time, we will never be able to develop innovation. So we have understood, and for sure we need to understand that there is two aspects of the research. At first, there is agronomics, and on the second point, there is the efficiency of the economics and the development of the business model. I'm coming from NIO. I'm from a manufacturer point of view, so I have very well in mind the reality of the manufacturer and what needs to be the business behind that. We just need to avoid to merge too soon the two aspects to be sure that we are not going to miss some opportunities associated to robotics in agroecology. But we also need to have in mind all of the other aspects. And Grand Défi is quite larger than what I've shown this morning about agroecology. That's just a part of the initiative.
Yes, thank you very much. I'm sorry, we are just a little bit in late, but anyway, you will have the opportunity to ask some more questions to Cédric during the coffee break and maybe during the 3 days of the FIRA. So thanks again, Cédric. Okay, and now let's switch to the second speaker with Leandro Zaza. And I let you introduce yourself about developing software-defined machines in a collaborative way.
All right. Thank you very much for having me here. So my name is Leandro Zaza. I'm from TTControl and cover different roles. Among them, there is also the role of AOC manager. AOC stands for Autonomous Operation Cluster, as you can see on the top right of my slides. So what we are going to talk today is a technological approach which we are pursuing in order to have software-defined machine in the field and a proposal on how to collaborate in order to reach this kind of goal. Before going in the details, I want to have just one slide about my company. So TTControl is a joint venture between the HYDAC and TTTech. So HYDAC is a well-known, let's say, hydraulic components supplier, and TTTech is a company from out of Austria, actually active in different sectors, spanning from the industrial, avionics, aerospace, and automotive. So we are a joint venture between these two big companies, and we are focused on the off-highway market. So we provide solution, control units, gateways for this market. Okay, so yeah, I hope you can read my slides because I think they are out of focus. So, being active over 20 years in the field, we see different trends. So definitely one trend is the autonomous operation, so how to automate the machines, how to make these autonomously operating in the field. Then we see definitely also a trend in the cloud, the telematic solution. So all the data out of the vehicle is uploaded in the cloud for fleet management, for vehicle management, but also for AI and to deploy AI algorithm on the cloud. Then definitely we see the trends moving from, let's say, the low latency or low speed CAN interface, going to more towards the Ethernet and multi-gigabit Ethernet interfaces. And last but not least, also a strong push for safety and security. So safety is already a long time in the market. Now the next trend is the security, and this gets even more important. So how to avoid that there is a cyber attack in the machine which is autonomously moving, maybe in the field, and causing also damage to person. So on the autonomous parts, well, a very simple definition of robots, you may know better than me what is a robot, but on the right-hand side I have just a screenshot of a McKinsey research which shows that agriculture has a potential of, I don't think it's readable, but of 57% of operations which are in the agriculture sector can be automated. This is all good, all nice, but reality may look different, because in the operation, a real operation, the robots need to work in a harsh environment. So not only in sunny days, but also in days where fog, ice, different light condition. Then you need to operate in an environment which is constantly changing. It's per definition changing. You want to change the environment with the robots in agriculture. And there is a variety of use cases. So there is not a single use case that you can address with a single robot. You need to have a robot which is able to fulfill different use cases. In terms of functions which are needed to accomplish this task, we definitely see the object detection, so a possibility to identify or to distinguish between, for instance, plants and weed, to identify people, and this comes together with safety, so around the robot, we should make sure that a person is identified, avoiding a collision with this person. Navigation and SLAM. Of course, a robot needs to move in an unpredictable environment autonomously to identify and calculate the best path and to avoid any collision with the object in the surrounding. And last but not least, also the job planner. Of course, a robot needs to accomplish a task, a job, and it needs to make it in the best and efficient way. On the system level, we definitely see the presence of standard control unit, which can already perform basic automation, but when it comes to enrich the automation level, camera needs to be introduced. And this comes together with computer vision and AI algorithm, so artificial intelligence algorithm. On top of that, and to increase the safety level, you need to have also multi-sensor modalities. So probably camera is not enough, no longer enough to distinguish object in every environment, in every condition. Probably you need to have also LiDAR or a radar, and you need to fuse the data. So it's not only possible to detect an object through a camera or through a LiDAR, but you probably need to fuse the data of the camera and LiDAR, for instance, and apply the algorithm on this fused data. And this it's called low-level sensor fusion. Then, as next step, you need to connect the machine. You probably need to upload the data out of the machine, out of the camera, out of the LiDAR to the cloud. Perform there the AI algorithm, so your neural network needs to run on the cloud, and then you want to deploy the trained network on the machine. And another trend, another need is to have a vehicle-to-vehicle communication. This can happen on the cloud. So in this architecture, vehicle architecture, you can realize there is a strong and central computing box, HPC, where we connect all the sensor and all the other ECU in the system. So the differentiator, and this is de facto state of art, the differentiator in the future will be the software. So the software which is incrementally uploaded in the machine, enabling new functions, increasing the capability of the machine itself. And that's why we talk about software-defined machines. So machines whose capability are enlarged thanks to incremental upgrades of software. But still, there is a centralized hardware, and you deploy all the new features over the air in software. What are the challenges to do that? So definitely, it's beneficial for the off-highway market to look at the automotive, to see what they are doing, to leverage their experience and avoid committing the same mistakes. The software-defined vehicles also comes with a strong push of software modularity and flexibility. So you want to be prepared at the very first day how to consider incremental updates, how to manage them. There is also limited in the community of experts, so we are all lacking of forces for engineers, software developers, embedded software developers, and there is also a limited data set for training, in order to train the AI algorithm. You may look also at synthetic data, so you may digitally create new data in order to simulate the environment and run on that environment the AI algorithm. So all this, so there is a big there are big challenges. There is an extremely push for software-defined vehicle. So at TTControl, we are trying to solve these challenges with a new approach, which is a collaborative approach. So we believe that it's not possible that a supplier-customer relationship will solve all the issue, but we need to collaborate between supplier and OEMs. And that's why we started 3 years back now, a project which is called Autonomous Operation Cluster. The Autonomous Operation Cluster is a project where multiple OEMs are working together, defining the building blocks for the autonomous operation vehicle, for the software-defined vehicles. They are collaborating together and sharing experience, sharing know-how, building up new functionalities in the machine. And we are lacking the agriculture. That's why I'm here to invite you also to this autonomous operation cluster. What we are doing, since the software is key, and in order to enable incremental and constant software updates over the year and over the air, we started from a middleware to deploy a software middleware which enables you in the future to upgrade the machine. And this is a ROS2-based middleware, which is strongly hardware agnostic. So as of today, we can work on ARM-based solution, x86, as well as NVIDIA platform. In the future, we will be also able to support additional big SoC. But basically, the concept is being hardware independent. It's a ROS2-based, as I mentioned. We deploy also DDS, which is a very fast communication protocol between tasks to make sure that these tasks are all synchronized. And we developed also the building blocks to enable, as I mentioned earlier, software-defined vehicles. And this comes together with the entire pipeline, the AI pipeline, which is not only deployed on the edge, but can be also deployed in the cloud. So coming from data, so data is collected, is annotated in the cloud, then the model is trained, is profiled, it's exported, then the code is built, tested, packaged, then deployed on the machine, configured on the machine. We monitor the results of the software in the machine during the operation, and then the loop comes back. So all this, so we put in place all this infrastructure to support the software-defined vehicle on the cloud as well. So I'm going already to a conclusion. So I share with you the trends that we see in the autonomous operation. So a system overview. So there is with a centralized high-performing computing platform where all the sensors, all the peripherals are connected. But this is not the essential point. The essential point is how to develop software-defined vehicles by incremental updates over the air. What are the challenges which this comes to? So there are a lot of challenges that we need to solve, and we believe that these challenges cannot be solved in a one-to-one relationship, but it needs to be done with a community, in a community. And the community which we propose is the Autonomous Operation Cluster, where we are already building the blocks for enabling you software-defined vehicle in the future. And with that, I'm the end of my presentation. Thank you very much.
Once again, we are a little bit in net, not so much. While Miguel goes into the desk to set up everything, we have the time for a short question. If anybody have a small question, quickly. Yes, of course.
Yeah, I have a small question. When you start talking about collaboration, I was wondering, you are talking about collaboration between all the producers and in that line, but is your community already working on collaborative robots? And what kind of concepts should be adopted behind that?
Yeah. So thanks for the question. So yes, when I talk about collaboratives, yeah, I mean really hands-on on the single code. So we have a community where we share the software codes among all the partners. And among these partners, there are partners which have robots. So for instance, I mentioned before, I showed the logo of Rosenbauer. Rosenbauer is a firefighting vehicles. They have robots which moves in an unpredictable environment behind the line of sight. So beyond the line of sight. So, and for that application, we are developing this middleware and the software for that. So yes, we are tackling this, the robots as well. I don't know if this answers your question.
Okay, thank you very much. And again, if you have some questions, let's use the coffee break to ask. And the forum, the International Forum on Agricultural Robotics, is a forum, and you will have 3 days to discuss and exchange some point of view. So thank you again.
Thank you.
And now we're going to talk about cooperation between aerial robots and terrestrial robots with Miguel Marquez. So let's go ahead.
Thank you. Good morning, everyone. So I'm Miguel Marquez, and I would like to thank my previous colleagues that talked before me, because most of my points, they are already covered, and they have already covered it, and they will make my presentation easier. As you see, there are lots of common points. And it was a pleasant surprise to see that all the community is looking at the same way. Okay, so there is. So a brief outline of the presentation. First, I'll do a little research context, talk about where I come from. I'm from Inesctec in Porto, Portugal. Then I'll go into a manned aerial vehicle and ground vehicle cooperative in long-term operation, and how that affects 2 key points, that is robotic mapping and monitoring of environmental elements, and how those are affected by using aerial and ground vehicles in conjunction. And we'll finish and open for questions. So first, a little bit of context. Inesctec is based in Porto, Portugal, and it was funded looking into Portuguese reality, and in conjunction with the robotics strategic agenda of the European community, and into precision agriculture. As my previous colleagues already talked about, soil compactation is an issue. So we intend to build smaller, modular, safe, autonomous vehicles to develop and research. We are a research community, and we also provide, so we also research and develop modular and smart IoT sensors for actuators. So as the first presentation already talked about, so we act into making smart tractors and smart machines for the machines that are on the field right now, and looking into the future, so for future machines that will be used in years and decades ahead of us. And 3 examples of fields that we actuate, we research. So permanent woody crops, such as Douro's vineyard. If you've tasted the Douro, the Porto wine, so that's where they come from. Protected crops, such as greenhouses, and forest biomass, especially in forest fire prevention. And so a little bit of general knowledge. So for unmanned robotics, automated robotics, there are 3 main issues that need to be addressed. First, map and path planning. Again, one of my colleagues already talked about that. So you need to have a map of your whole crop in order to plan your actions, the robot's actions. And you also need to take care of safety. So the actions of the robots, the autonomous vehicles, they need to be safe for the environment and for people around it and for the plants. And you have to take the right agronomic decisions. So you need to gather the right data and use that data to know when, how, and what amount of actions you're going to take in order to have the best results. So, looking into safety, safety is especially critical if you think about unmanned vehicles. And safety can be enhanced by fusing aerial and terrestrial perspectives. So as you can see on the picture in the higher part of the slide, you see a terrestrial robot perspective that was a camera embedded into a terrestrial robot. And on the lower part, you can see the same exact scene looked from an aerial perspective. And you can see that some elements, they are recognized, they're identified in the terrestrial perspective and others in the aerial perspective. And you can see that they can be fused. Again, another concept that is shared among presentations. You can fuse information to have a better understanding of your environment, especially in security, in safety. So looking into the cooperation, so the system that we propose is using an aerial vehicle connected through a tether, so through a cable, cable to the ground vehicle, and through the cable, the ground vehicle sends energy to the aerial vehicle. So the aerial vehicle, the drone, has an embedded battery for emergency, but the most part of the energy comes from the batteries from the ground vehicle, and that allows for long-term operation. So you can use the aerial vehicle during the whole operation on the field, during long hours. And that allows the aerial vehicle to identify elements and to track elements, moving objects, and to track the terrain during the whole operation. And you have a plus that you can build semantic, topological, and vegetation maps using live. So even if you deploy this system in an unknown scenario, it still can operate because it can create the map that usually uses satellite images. It can create live during the operation. If you look into, if you look into robotic mapping, you can think of the amount of agronomic information that you can get from one single plant. And if you expand that to a whole crop, you can imagine that the global map or the map of the whole crop is really dense with information. So it can get larger than the amount of RAM memory that you have in your robot. So you cannot allocate the global map, the map of the whole crop, in the RAM memory of your robot all the time. So there are two simple solutions. You can either use a local map with all the information, so you use a partial map, or you can use a global map, but with less information. So you discard some of the information that you have collected. And both of them are not ideal. So what in INRAE we propose, and what you can see right here at FIRA at work, is the Navibox. So the Navibox, as one of my colleagues already stated, is the idea of putting all the technology, the software, into one box that can be connected to a vehicle, either being a new smart vehicle in development or an old vehicle with modern sensors. So you can sensorize a vehicle and use the Navibox to make it autonomous. It is focused in 3D mapping and location, and in path planning, especially safe path planning. Come on. Sorry. That is. Okay. So, looking into robotic mapping, as I said to you, the solution that the Navibox uses is to use the global map as a series of as a graph map. So as you can see in the picture in the upper part, it is a graph map, and it is stored in the mass memory, in the hard disk of the robot, where you have a lot of space. And then the local map are the nodes. Each node is a local map that is transferred to the RAM memory as the robot progresses through the graph. So this way you can keep all the information that you have gathered of your crop, of the plants, and you can use that information as you progress through the operation. And if you think about path planning, that's the second point of Navibox. Navibox uses the mass, the center of mass of the robot and the inclination of the terrain in account in order to do safe path planning. Because what we see, especially if you look into, if you have ever been to Portugal and to Porto, you see that the vineyards are really, really steep. So there you cannot use a robot that does not take into account the center of mass. And with that, you can cause, if you don't take into account that kind of information, the robot may tumble and cause accidents. So this is the reference of the paper that we published, and you can also see that in action right here at FIRA. There's a slide about the demonstration that will happen of some robots that use that technology. Okay, so here a short video of the fusing of information from aerial perspective and a terrestrial perspective. So as you can see, not all the time the terrestrial perspective is able to catch the whole environment around the robot. That is critical, especially for security issues. So you can by fusing information, and that is only a camera, and we propose using a camera and a LiDAR, as one of the previous speakers have already told. We propose using that to fuse information to have a better understanding of the environment. So these three points, they can be enhanced by using aerial vehicles and ground vehicles in cooperation during the whole operation. And that's the platform that we propose, and that's what we are researching. And that's the platform. So that's the platform that we propose, and you can check the Navibox into action at those two demonstrations. So Thursday on the morning and on the afternoon, you can check some robots developed by, some ground robots developed by Ineshktech and by Tribe Laboratory into action. So with that, I conclude and open for questions.
Thank you very much. Just before checking for question, I have to check if Paul Chambon, the next speaker, is here, or somebody from Hexagon Teria for the next speech. Well, so we have time for one or two questions. Is there any question for Miguel?
Over there.
Yes.
Hi, thank you. Thank you for the very nice presentation, Miguel. I have a quick question regarding the Douro region. They are very steep indeed, and I've heard that sometimes you're sort of GPS deprived, or you don't have global positioning. So I wonder how you manage that.
So we use LiDARs and the cameras to create a map of the environment, a topological map, and the LiDAR is especially useful because you can create a map of the crop, and you use your position inside the crop to locate yourself. So you use SLAM, as one of the previous speakers have already told. You use SLAM to locate the robot into the ground robot into the crop, and you use the image from the aerial vehicle to locate the aerial vehicle in regards to the ground vehicle. So that way, even if you don't have the GNSS, you can still have your robot located into around the crop, so you know where in the crop it is, and the aerial vehicle in regards to the ground vehicle.
Thank you very much. And maybe we can take a second question. Yes.
As well, thank you for this great presentation. In the end, I think I have two questions. One is, at least this is legislation in Germany. You are not allowed to proceed with the UAV without an operator. Is it somehow addressed as well in your scenario?
Yeah, that's as the legislation is changing. So this is the research for this research is aimed at the future. So in 10 years, in 15 years from now, this research will be mature, and so this is in a prototype phase. So it's in the research phase. So we are publishing papers about it, and we are preparing the basis for the future. So in the future, we don't know how the legislation will work, and that's one of the issues that why we want to focus on security. I focused on security so much in my presentation, because if we can prove that the autonomous system, aerial and ground system, is safe to the legislators, we can, maybe they will be convinced that they can operate autonomously. So we are aiming on that. But that is a research that is starting, so that is still in the beginning, and it's aimed in the future, in 10 years from, so 5-10 years from now.
So thank you very much, and do not hesitate to ask some questions during the coffee break. And thank you again. It will be time to switch directly to the last speaker of the session, who is Jorge Aviles. So, Jorge, please. Go ahead. Thanks again. And our last speaker of the session will be Jorge Aviles, talking about merging row following and GPS-based navigations. It's okay for you, Jorge?
Yeah. Good morning. My name is Jorge Aviles, and I'm excited to share our research in autonomous navigation, especially in agricultural environments. I would like to start to mention that autonomous navigation is one of the most challenging tasks in robotics, in particular in agriculture, where we have different problems. The first one is that agricultural environments in general are not unstructured environments. It means that when we require a robot to perform some task or application, usually these applications are not predefined, and also it involves some obstacles, some objects that are not planified previously. Then, if we focus in particular sensors like GPS or cameras, we have some problems. For example, for GPS, we have accuracy that most of the time is not the best for these applications. The biggest the accuracy, the price is going to increase for the sensor. And on the other side, we have, for example, cameras. With cameras, what happens if we are working in a cloudy day? The performance is going to decrease. Finally, weather conditions. Most of the applications are performing outside, in outside environments, where we cannot control illumination conditions, for example. To solve these problems, there are some solutions that have been implemented. For example, the first one is remotely piloted, which requires human intervention to guide the robot. Then we have pathways, which is a hard restriction for this kind of application. And finally, we have the most used, that is GPS. However, there are some disadvantages, as I mentioned before. and also some vision and ranging sensors. So after discuss the problems that we have with the different sensors, this is our proposal. We were discussing what happens if we take advantage of the benefit points from cameras and we merge this information with GPS. And this is the result. For example, here is a typical example for crop navigations. Here, it is part of a competition when we participated last year. Here we have 4 parcels that we have to complete completely autonomous. For this, we can distinguish 3 zones. The first one corresponds with the parcels where we have different crops and different distributions. Then, to transit from parcel 1 to parcel 2, there is a transition zone where we don't have crops. And finally, in order to change from parcel 2 to parcel 3, we have to make half turn. So, for our proposal, we can divide in 7 steps, 7 stages. 1, 3, 5, and 7, we are using vision-based navigation. And for number 2 and number 6 also, but we changed the perspective that it is called bird's eye view transformation. And finally, to make the half turn, we are using GPS data because we don't have visual information in this case. So we are going to start with visual information. What happens when we have visual information? From left to right, first we have the input image that is given by the acquisition system. The acquisition system is here in the platform, in front of the platform. With this acquisition system, we are able to detect different kinds of crops. For the competition, we focus in maize and bean. Then, after that we receive the input image, we apply some different thresholds in order to separate vegetation and, in particular, crops from the background. After, we estimate the lines, the crop lines, as you can see on the top right. And if we project these lines on the image, they are going to meet in a point. This point is called vanishing point. And the navigation strategy is to maintain this point in the center of the image all the time. In that way, we are going to correct the trajectory. At the bottom, we apply different models to our experimental platform in order to transfer the visual information that is in front of the platform to control the platform. We have to transfer using different matrices. And finally, we are going to estimate 2 different velocities, the linear velocity and the angular velocity. The angular velocity is to change the direction, and the linear velocity is the speed that we are traveling the parcel. Now, what happened in transition zones? In transition zones, we don't have crops to be detected. In this case, one more time, we have the input image, but first, we are applying a transformation. It is called bird's eye view transformation. The reason why we are using this transformation is because there are some benefits. First, we are emulating a virtual camera that is fixed in this position. With this information, we can identify the distance from our actual position with respect to the field, as you can see in the second image. And also, we have a better perspective with respect to the other parcels. Then we apply a color space transformation in order to increase the robustness of our proposition. And finally, we detect the crop parcels and the contour. In the same way, we apply visual servoing, which, using visual information, we are guiding the platform. In the same way, we are estimating linear and angular velocity to correct the trajectory. No. Okay. And what happens when we are at the end of the parcel? In this case, we don't have visual information, we don't have crop parcel information to use visual information. In this case, we are forced to use GPS data. First, we have to identify the end of the parcel. For this, we are using one more time different computer vision techniques in order to estimate the end of the parcel. Once that we are in this part, in the image you can see the last crop that we are detecting. And in this point, we have to switch to another control strategy where we are going to use the GPS coordinates to transit from parcel A to parcel B. In this case, first we have to live in the parcel, of course, without ruining the crops. This is the priority for any agricultural application. For this, we have to go out to the parcel, and after, as we know previously the coordinates, we propose a trajectory to guide the platform. And once that we define this trajectory, we apply a technique that is called model predictive control, where we are using the model of the platform in order to predict the future behavior of the platform. In that way, we are going to position the platform and we are going to follow the trajectory. Once that we are at point B, we are going to recover the vanishing point estimation, because now in this point of the parcel, we have one more time visual information in order to exploit this data. Okay, here are some results that we obtained from simulation and also experimental results. First, I would like to mention some important points about simulation, because we are using a very realistic simulator that is called Gazebo. In this, we can integrate our platform, we can emulate the experimental conditions, like the kind of crops, the distances, and the distribution. For example, we have 3 lines, 2 lines. We can recreate everything that we want. And in experimental results, as I mentioned before, we participate in an international competition in realistic conditions, where we obtain the trajectory that it shows to the right. And here in this image, as you remember, the trajectory correction is based to maintain the vanishing point in the center of the image. So the results are all the time around this value that correspond with the center of the image. Before conclude, I would like to show a short video. It is. Thank you. To the left, we have the vanishing point estimation, as you can see. For maize that is in advanced growing stage, we evaluate our proposition in different stages, different crops. Here are the results. In the right, we have the half turn that it's deployed by the experimental platform. And at the bottom is the autonomous, all the time it's autonomous navigation, but from different perspectives. As you can see, there are realistic conditions where we obtain the results I presented previously. And to conclude this presentation, maybe you are thinking what happens if we apply this method to different crops. So that's not a problem. We test our proposal in different crops at different growing stage, as you can see in the video. Second, because we are estimating vanishing point, we are able to estimate for 3 lines, 2 lines, 4 lines. It doesn't matter how many lines we have on the field. We are able to estimate the vanishing point. One of the advantages to merge visual information and GPS information is that we have a completely autonomous navigation. Some of the robots that we have today are able to operate just using GPS data. But what happens when we are not enough information to deploy this solution? we are going to have some problems. So we can set that if we have visual information plus GPS information, we are going to have fully autonomous navigation. Then, one of the most important points of this approach, because we are integrating visual information, it allows to protect the crops. Once that we detect that we are near to the crops, we can correct the trajectory in order to protect the crops. And finally, model predictive control is one of the alternatives to follow different trajectories. And this is important because model predictive control allows to integrate some restrictions like velocity, like force of the experimental platform. And this is a very, very important point. So thank you so much. And if you have questions.
Thank you very much, Jorge. We have time for one or two questions. Does anybody want to ask some question to Jorge about the fusion of several sensors to make raw navigation? Yes, actually, I have one, of course. Because you show us a different kind of strategy, but you didn't mention how do you switch between the strategy. Is it automatically done? Or do you have planification? And how does it work?
We have a planificator that I didn't mention, that is like the brain of our approach. And this brain, it's going to manage when we have to use visual information and when we have to switch to GPS data.
Okay, thank you. Another question? Yes?
It's on the same question, but do you specify a GPS position for the switch? You know that you are at the end of the line, or your plant detector is able to understand that it's the end of the line and switch automatically to the path following?
Our vision algorithm is able to detect the end of the parcel and switch to the GPS following.
Okay, so let's thank Jorge again.